All right, so hopefully you're doing well today. Today we're doing bond dissociation energies. This is a real quick video because we've done this before in general chemistry, so um, it's there's not too in depth. But if you have questions, of course, let me know. So energy needed to homolytically cleave a chemical bond, like a covalent chemical bond, is the definition of bond dissociation energy. Okay, so for example, we got H2, so HH bond. We got that bond cleavage. Homolytic cleavage gives two hydrogen radicals. Okay, so remember we're using those fishhook arrows for that mechanism. And this delta H value, the enthalpy associated with this is 435 kilojoules per mole. And this is an endothermic reaction. So remember, anytime you're breaking chemical bonds, it's an endothermic reaction. And then anytime you're forming a chemical bond, just like we are here, it's negative, and negative 435 kilojoules per mole is exothermic. Remember, this is equal and opposite magnitude of the bond cleavage of this hydrogen bond. Okay, so a couple more definitions or trends. We want to look at how the stronger the bond, obviously, the higher the bond dissociation energy is going to be. And so that would be like a single bond compared to a double bond compared to a triple bond. But also, we have a trend among halogens, which is important for the next chapter. For example, when we have halogens or haloalkanes. So increasing size of the halogen goes from fluorine to iodine, right? But then as we go from right to left, iodine to fluorine, we have an increase in bond strength. And that's just because of the size of that halogen. There's smaller, fluorine matches up better with the chlorine, and so you get better bond overlap. That's all we really need to know. Now moving on to the formula for this. So delta H, the overall enthalpy change of a reaction, is equal to the sum of the bonds broken plus or minus the, I like to put minus the sum of the bonds formed. And so I'll explain why I like to put minus instead of plus in just a minute. It really is up to you, just kind of keeping an eye on the signs of your bond cleavage and formations. Okay, so give you one example. We've got bromoethane plus water goes to ethanol on HBr. Okay, so what happened here in this? We got to tally things up. Nothing really happened at those two hydrogens. They're still present. The only thing that we did do was we broke that CBr bond to form that COH bond, right? So if we broke that CBr and we're referring to our chart, we can see that that has a bond dissociation energy equal to 285 kilojoules per mole. That OH bond being broken to form that new OHC, or that COH bond, that OH bond is worth 498 kilojoules per mole. And then now that's all that we've broken on the left side. And so the bonds formed on the right side are made as the COH, and that is negative 393 kilojoules per mole. And we also made an HBr bond, which is negative 368 kilojoules per mole. Okay, so these are negative because they are releasing energy. Anytime we're making bonds, we are releasing energy. And so that's why I put sum of bonds broken plus or minus the sum of bonds made. It just depends on what you want to do. If you look at the chart just gives you a value, and it's up for you to decide if it's positive or negative. So if you leave that sum of bonds broken minus sum of bonds formed, you don't have to think about the signs of those, right? So for example, if we just have just positive 285 plus 2498 in parentheses, and then we subtract 393, and then we also subtract 368, then it kind of works out. So you can either add the negative values or you can subtract the positive values. It's the same math in the end, and you get a positive 22 kilojoules per mole. And that's all she wrote for bond dissociation energies. get some more practice if you want, but we've done this before.